I would like to start by thanking the organizers, and in particular, Professor Alberto Isidori, for this opportunity to present an introduction to the ideas of input to state stability. My plan for this talk is to first introduce input to state stability, including its role in feedback design, and to provide statements of the main theoretical results about ISS. I will then discuss associated notions such as input to output stability, detectability, and integral ISS. And I will conclude with a brief sampler of theoretical tools and a couple of sample applications. The overall theme of this talk will be that of ISS, which deals with stability-like questions for systems with inputs and outputs. There are many reasons for studying such questions. One of the strengths of systems theory is in providing a methodology for analyzing complex systems when viewed as an interconnection of simpler devices. And ISS tools are often useful in that context. In particular, ISS provides one way to quantify system responses. Yet another motivation is more purely mathematical, namely the unification of state space and input-output stability notions. Regarding the first motivation, the study of systems through decompositions, note that even if we wish to study a closed or autonomous system, we must allow for the subsystems to have inputs and outputs, since otherwise one cannot even define interconnections. Regarding the motivation of studying responses to external signals, of course, the inputs might represent, for example, disturbances or tracking signals, or in a regulator problem, various kinds of signals that we wish to follow. And the outputs might be measurements or error signals. Our first objective will be to provide a definition of input to output stability, which takes into account internal states and transient behaviors. Actually, for simplicity, I will only talk about input to state stability, and I will introduce outputs later. In addition, I will only address notions of global stability with respect to equilibria, but many of the concepts and results may be extended to local stability and to stability of attracting sets, such as periodic orbits. And there are robust stability versions as well. The talk will focus on theoretical results, and I will not cover in any detail the many applications which can be found in papers and textbooks. For systems without inputs and outputs, the classical notions of stability were introduced by Lyapunov well over 100 years ago. On the other hand, George Sames and many others developed a rich theory of stability for input-output operators starting in the mid-1960s. The notion of ISS allows us to combine features of both. For linear systems, the combination is not an issue because internal stability implies all types of input to state stability, such as convergence of states to zero when inputs converge to zero, bounded input, bounded state stability, and finiteness of operator norms. But for non-linear systems, matters are more complicated, as illustrated by this example, which is exponentially stable when the input u is identically 0, but which exhibits unstable behavior when forced by an input which converges to 0. The x squared term affects the system when the input is not 0, dominating the stable real part, but it has no effect on the unforced system. So we must explicitly impose boundedness by asking that the amplitude of the state be ultimately bounded. We express this condition by means of k-infinity functions, that is to say, using a nonlinear increasing function of the amplitude of the input. I will mostly talk about input to state behavior, but I will later mention extensions to the more general case of outputs, and I will also discuss other norms than subnorms. In order to finish introducing the notion of ISS, let me first remind you of some formalisms. Global asymptotic stability of the origin of an unforced system is usually given as an epsilon delta definition, but a totally equivalent way of defining it is by using KL functions. That is, one postulates that the solution must be bounded above by a function which increases in the first variable and decreases on the second variable. This restricts overshoot and forces solutions to converge to the origin. We can now define ISS. We just ask that an estimate like this holds, and the sum could be used instead of a maximum equivalently, of a KL term that handles the effect of initial states when t is small, and an input gain term that is effective when t is large. This gives exactly global asymptotic stability if there are no inputs, and in general, says that the overshoot depends on the initial state and the asymptotic behavior depends on the size of the input. ISS is obvious for stable linear systems, since variation of parameters gives us an ISS estimate using linear gains. The estimate has an additive form, but one can equally well define ISS using a sum instead of a max, just changing slightly the beta and gamma functions. To show why ISS plays an important role in feedback redesign, let us consider the following problem. Suppose that a system has been stabilized under feedback in the sense that a closed loop system is stable. It may well happen that actuator disturbances destabilize the system. This may happen even in a simple feedback linearization example. Suppose that we cancel the nonlinearity and feedback a linear function of the state. This works fine if there is no disturbance D, but if there is a disturbance, then we are back to the counterexample that I mentioned earlier, in which a stable input destabilizes the system. The interesting fact is that if we redesign our feedback law by just adding a linear term, then the new closed loop system is still stable, when there are no disturbances. But in addition, it is now ISS because the cubic term dominates the disturbance. In fact, a general theorem says that whenever one can stabilize a system, it is possible to redesign the control law so that the closed loop system is input to state stable with respect to actuator disturbances. In particular, every feedback linearizable system can be made ISS. This is just the tip of the iceberg. There is a beautiful theory of recursive design based on backstepping and other techniques that exploits these ideas. Now that I introduced ISS, let me discuss some of the basic theory. One may argue that a mathematical notion will be useful if it is natural, in that it can take many equivalent forms. So let me briefly discuss how ISS is exactly equivalent, among other properties, to the existence of robust stability margins, to dissipativity, to a combination of stability and finite asymptotic gain, and to an energy-like stability notion. The theorems that I will mention will all hold under minimal assumptions for finite dimensional and time invariant continuous time systems. Generalizations to time varying systems, to stability of more complicated attractors than equilibria, to discrete time systems and so forth, have also been pursued to various degrees, but I will restrict attention to this case. The first theorem says that ISS is equivalent to robust stability in the sense that there is a margin of stability, which is large for states far from the origin. That was what K infinity means in the comparison function. And the system remains globally stable under all feedbacks whose magnitude is bounded by this margin. Observe that for linear systems, a matrix remains Hurwitz under small perturbations, so margins always exist. In that sense, ISS is a better generalization of linear stability than plain global asymptotic stability. As we already saw, if a system is ISS, then the unforced system is stable, and it is also clear, since the overshoot term dies out for large t, that the state approaches a ball whose radius is determined by the size of the input. It is a surprising and non-trivial result that the conjunction of these two properties is in fact equivalent to ISS. Mathematically, the challenge lies in the fact that the ultimate bound is not required to be uniform on inputs, and there's no convexity and compactness to help, even in the sense of weak topologies. A third theorem says that ISS is equivalent to the existence of an ISS Lyapunov function, which amounts to a dissipation inequality with a smooth storage or energy-like function, which is allowed to increase at a rate bounded by the instantaneous input magnitude and which otherwise decreases. Note that for systems without inputs, the U-term vanishes and the theorem reduces to the classical converse Lyapunov theorem. Another way in which ISS is natural as a notion of stability is that every serial connection of ISS systems is again an ISS system. In particular, driving an ISS system by a stable system produces a stable system. This fact can be easily proved directly, but it is especially evident from a dissipation characterization. Given appropriate storage functions for each system, their sum is a storage function for the cascade. The positive input term of the Z system is canceled by the negative stability term of the X system. More generally, feedback does not destroy stability if the feedback is small enough that V still decreases. which leads to a most useful small gain theorem for ISS. It is worth looking at a simple toy example to understand how ISS ideas can help in feedback design. Let us take the textbook problem of angular velocity stabilization of a rigid body with two torques as controls, which under a coordinate change becomes a cascade of a one-dimensional system described by x1 and a linear system. The x1 system is clearly stabilizable when thinking of x2 and x3 as inputs. So the basic redesign theorem says that we can make it ISS, which then implies, because of the cascade result, that the complete system can be made ISS as well. If one carries out this idea, the net result is that the feedback law shown here globally stabilizes the rigid body model, and moreover, does so in an ISS manner. This is shown by looking at the closed loop system in slightly different coordinates, in which the system can be seen as a cascade of two ISS systems. The cubic term provides a margin of stability for the x1 system, and Z2, Z3 give a stable linear system. This is just a simple example of a systematic approach to constructive feedback design based on ISS ideas. Finally, in this brief discussion of characterizations of ISS, let me mention a last theorem, namely that ISS is also equivalent to the existence of estimates of an integral to integral type, analogous to an H-infinity estimate if all nonlinearities were quadratic. On the other hand, and very surprisingly, a genuinely new concept finally arises if we mix integral and subnorm estimates. This concept of integral input to state stability is strictly weaker than ISS, and I'll say a few words about it later. Let me now turn to input, output, and detectability properties. The notion of input to output stability is defined for systems with outputs in a manner totally analogous to ISS. One just replaced the estimate on states by an estimate on outputs. Using KL functions to bound an initial state-dependent transient behavior and a K-infinity function to express the influence of input magnitudes. ISS is a special case, of course, when the output is just a state. Observe that the overshoot is controlled by the initial state, and this is what we want, since in regulator problems, for instance, the mismatch between an internal model and an external signal determines the transient behavior. One may characterize IOS in dissipation terms, but let me skip the technicalities. Yet another ingredient of the theory is the notion of zero detectability. One might define detectability by asking that identically zero input and output signals imply that the internal state converges to zero. However, it is far more reasonable and not equivalent when dealing with nonlinear systems to ask that small inputs and outputs should imply asymptotically small internal states. The notion of IOSS makes this precise, including, as always, a term that quantifies a transient behavior, and incorporating a term for the amplitudes of inputs and outputs. For large T, the beta term goes to zero. So if U and Y are small, then the state is eventually small as well. IOSS stands for input and output two-state stability, consistent with the idea that small inputs and outputs imply small internal states. Also here, a fundamental theorem states that IOSS is equivalent to dissipativity with smooth storage functions in the expected sense. One can prove that the IOSS property is in fact necessary for stabilization under partial observations. There is a fundamental relationship among the three concepts which I just introduced, saying basically that external stability and detectability together are equivalent to internal stability. Intuitively, if inputs are small, then input-output stability tells us that the outputs are also small, and then detectability ensures that the internal states are small. But the main point is that the equivalence holds for IOS, IOSS, and ISS as we define, and this is yet another indication that these are the right notions. There are many other subjects which I could cover regarding the ISS formulation of systems properties. Let me mention a couple of them now. As I said, mixing integral and pointwise estimates results in a genuinely new notion, that of integral ISS. There is a dissipativity characterization that goes along with integral ISS, and one can prove that this property is strictly weaker than ISS. For instance, bilinear systems, which are stable with inputs of 0, are always integral ISS, but are seldom ISS. Integral ISS corresponds to a sort of partial dissipativity together with weak detectability, and it has proved useful when studying mechanical tracking problems, where the dissipativity property can be checked using energy functions. Finally, let me point out that one can define a notion of minimum phase system in the sense of input to output stability of the inverse system, or an ISS property for zero dynamics. This notion plays a role in adaptive control, for instance. I did not discuss proofs of theorems, nor do I intend to do so, but let me show you a couple of examples of some of the issues involved to give you a flavor of parts of the theory. For ISS systems, differential inclusions arise when inputs are constrained by a stability margin. A key ingredient in the theory is a characterization of uniform global asymptotic stability by Lyapunov functions. A Hamilton-Jacobi partial differential inequality, forcing directional derivatives to be negative along all constrained motions, is shown to have smooth solutions. This leads in turn to the dissipativity characterization of ISS. Another central ingredient is a relaxation theorem for differential inclusions, extended Filippov's theorem to infinite intervals. This gives us a corollary, the equivalence of non-uniform and uniform global asymptotic stability for non-convex differential inclusions, and the superposition theorem for ISS then follows. Non-smooth analysis is also beginning to play a role in ISS theory, although all the results that I mentioned until now were stated in terms of smooth V's. Non-smooth V's appear when discontinuous feedback is used, or when studying ISS properties with respect to observation errors, or in measurement to error stability. For non-smooth storage functions V, dissipation inequalities are understood in a viscosity sense. This means, in simple terms, that one must replace the gradient of V by generalized gradients, which amounts to using gradients of differentiable functions that just touch the graph of V, like the green one in the picture, which has the dotted line as tangent. And there may be many of these at those points where V has a corner. I don't intend to talk about applications in any detail, but let me just give you the flavor of a couple. One example of the general ISS philosophy concerns the control of jet engine stall modeled by reduced Moore-Greitzer equation and using only pressure as a measured output. The authors achieved this objective by viewing the problem as a robust stabilization one with the first stall mode as unknown dynamics. Their method relies upon a novel observer design coupled with the state feedback law designed so that three ISS properties are satisfied. The estimation error is ISS with respect to the unmodeled dynamics. The rest of the state is ISS with respect to the error and Z, and the unmodeled part is ISS with respect to the rest of the system. An ISS small gain argument is then used to prove that the design works. The next two applications of ISS are quite non-traditional. The first one concerns synchronization of chaotic systems, a technique proposed in the context of secure communications. It is interesting that ISS ideas may be used in validating designs. One wants a copy of the original system driven by the same input plus channel noise and starting at a different initial state to synchronize with the transmitter, provided the noise is not too large. One can state this objective as one of incremental ISS, and the preservation of incremental ISS and their cascades shows easily that, for example, the Lorentz chaotic attractor works. The second system tracks even though the signals are chaotic. The last example is also very non-traditional. It involves destabilization rather than stabilization in the context of mixing of fluids in a pipe. A central role is played by IOSS estimates, using as inputs the wall velocities and as outputs certain pressure differences. Here are cross-sections and longitudinal pictures showing the enhancement of mixing under the control laws. Of course, the authors did more than just checking ISS properties, but IOSS helped them formulate goals and organize thoughts. To summarize, I argue that ISS is a natural blend of Lyapunov and input-output notions suitable for the stability analysis of interconnected systems, that it can be characterized in many different manners through dissipation, stability margins, and so on, and that other system theoretic notions, such as detectability, can be formulated in a similar fashion, leading to an elegant and consistent theory. The theory, although deep and well-developed, is far from complete, and many exciting open problems remain for infinite dimensional and for hybrid systems, for example. I have not talked about applications in any serious way. I refer you to lectures and papers for details. Thank you very much.